Let's continue our notes in section 2.6 on the second derivative and concavity. So now we're going to look at some examples. So in the previous video, we just learned about what a critical point on a function or graph is. So number one, we are asked for each of the following functions, find all critical points, then use a graphing utility or a graphing calculator to determine whether the function has a local extrema at each of the critical points. And one thing I'll emphasize here is, well, what is a local extrema? That means a local max or min. So in the original graphs that we looked at up here, which of these graphs or functions have a local max or min? Awesome, this set here and this set here. So what we want to do for number one is to first find those critical points of our function. So those points where the derivative is either 0 or undefined. And then we're going to graph our function to see if we can tell if those points give us a maximum or a minimum. All right, so for number one, in order to find those critical points, we first need to find the derivative, f prime. So before continuing to watch the video, I'm going to encourage you to pause the video and work out the derivative of this polynomial. All right, then let's begin together. So using the power rule, we can differentiate that first term. So the 3 comes down, multiplies by the 1/3. So that actually cancels 3 times 1/3 to just be 1. So we're left with x. Then our power here reduces by 1. So we get x squared. Next term is similar. Using the power rule, we subtract 5 over 2 times 2. The 2's cancel. I'm left with 5, x to the 1. Next term, derivative of 4 times x just becomes the derivative, or just becomes 4. Again, we can use the power rule with our power of 1. And there we have it. Our derivative f prime of x is x squared minus 5x plus 4.
At x equals.
So let's first check if we have any undefined values. Is there anywhere on f that's undefined? Nope. We can plug in any x value we want and we will get an output for this polynomial. So now let's determine where f prime of x is equal to 0. So what we want to do is set 0 equal to this quadratic function that we found is the derivative x squared minus 5x plus 4. So now to solve for those x's, we can either use the quadratic formula or try to factor. And here our terms, our constants in front of our x values look pretty manageable. So let's go ahead and try to factor it. So please pause the video and try to factor first on your own before continuing. All right, let's take a look together. So what are some factors of 4 that when add together get us -5? Well, factors of 4 could be 2 and 2, but adding together gives us just 4 or 0. What about 4 and 1? Let's try that out. So if I take -4 minus 1, I add those together, I'm going to get a -5, which is what I want. And if I multiply them together, I get a +4. So I can put in my x's here. So my derivative factors into this form. So that tells us if I want this product equal to 0, one of them must equal 0 at least. So that gives me x minus 1 equals 0 or x minus 4 equals 0. So what does that tell us? Well, in the first case, x is equal to 1. In the second case, x is equal to 4. So my two critical points are x equals 1 and 4. So I'm going to summarize that here. Critical points are at x equals 1, 4. So now let's graph this function f of x in order to see if those critical points are at a local max or min. So one thing I want to emphasize here is that in order to determine what type of critical points these are, we need to graph the original function. We're going to look at the original function to see if those critical points are at a high or a low, a max or a min. So I'm going to move over to my Desmos graphing calculator in order to graph this function to see what type of critical points we have. So I'm going to go ahead and type in my function here. Please follow along on your own Desmos graphing calculator. All right, so here I just graphed my function f, and I went ahead and paused the recording so you didn't have to take the time to watch me type that out. But don't worry, I'm not super fast at it, so please take your time too. So let's look at what this graph looks like. So here's our graph. And now what do you notice about the points here and here? Well, the x value of this first point is at 1. We can see that when we tap. The x value of this point is at 4. Is that a coincidence? No, those are exactly those critical points that we found on our function. So what do we think? Do we have a local max here at 1 or a local min? What does that mean? That means around a small little neighborhood, if we want to look to the left or the right of this point, do we have a maximum? Yes, we do. So we have a local max here at 1. And what about this point at 4? A local min. So I'm going to go back to my notes and write that down. So at x equals 1, we have a local max. At x equals 4, we have a local min. And there we have it. Awesome. Great work, everyone. Go ahead and try the questions below and then follow the next video where we look at the next example.